Okay. So yes. So we were in our fourth lecture. We were discussing about computer arithmetic. Uh, Hi, Sarada. Are you there? Hi, Saeed Haider. Can you mute yourself? Yeah, thank you. Okay, so let's have a brief recap of what we did in the last class. In the last class, we basically looked at how to improve the performance of multiplication operation, and this can be done in two ways. Either you look for opportunities where you can have more than one bits to be taken at one time. So we can go for higher bases like base 4 or base 8. So we looked at one of the techniques of Booth's algorithm for base 4, and we saw that the multiplication operation completed in just two steps. It was fast, and we weren't concerned with the multiple of 3a, the tricky multiple of 3a in that case. We looked at the uh, hardware multiplier for Booth's algorithm for base 4 as well. Then we looked at the carry save adder multiplier tree. So the other technique to multiply is to have the operands, which are the partial products, added quickly. So we looked at technique called multiplier trees like Wallace tree and data tree, and they were using basic for full adders and half adders in their design, except for the last stage where there is uh, a full where there is a carry propagate adder or a ripple carry adder, and that completes the design. So in a CSA tree, the idea is to reduce the number of operands in every step. And then if you have got many partial products and you are going to add them, but the trick is that the bits are going to be added in a different way. So every partial product is going to be shifted accordingly, and then it's going to be added with some of the other partial products. So we looked at one of the designs of CSA multiplier tree as well. Then at the end we looked at array multipliers, and the idea behind array multipliers is to improve the performance using pipelining. So array multipliers are regular structures, and they have known delays, so you can easily break them down into stages, and it's good for pipelining that you have stages of equal durations. And then therefore RM multipliers take the benefit of high throughput, so they are going to give you high throughputs if you have many multiplication operations coming one after another. So that was also the design that we looked at in the last class. And then at the very end we looked at division operation. So we were continuing with the division operation, and a basic division algorithm could be to start dividing numbers, start subtracting the numbers till you get a remainder which is less than the divisor's value. So I'm going to just come back to division algorithm, and the problem with division was that it's a tricky thing. So we have two unknowns, and the basic equation that we are solving is our dividend is equal to divisor multiplied by the quotient plus s. So actually we are not doing any multiplication operation when we are finding the divisor. So these are the two unknowns. So we have these two unknowns here in the form of the quotient value and the remainder values. And since there are two equations to solve, two unknowns to solve, and then there is a single equation, there can be multiple answers. So we have another inequality here, which we say that the DE should always be greater than S, or in other words, the remainder should always be less than the divisor. So if we ensure this, then obviously it's going to give us a single result, because there can be Okay, so even if you're talking about like this, there can be different results if you just go for fractional parts as well. But let's talk about just integer parts. So if you have got an integer part here, so all of them are integers, then we can say that if these two, if this equation and this inequality is with us, then we can get a single answer. If you go for fractional parts, obviously you can have multiple answers still, right? So in fractional part, you can have still different answers satisfying both of these. Right. So, but in the last class, we didn't look at how to do division using an algorithm. So, the first algorithm that we are going to talk about is then going to be a restoring unsigned division algorithm. Right. So, we are first of all looking at unsigned division. When you're talking about unsigned numbers, you're talking about positive numbers. So, all of them are positive numbers. So, let's look at the very basic algorithm here, how to do division and what are the complexities involved over here. So an unsigned division is the easiest division to do, so we are going to look at this. And as we have said earlier as well, that when you're talking about division, there is another thing that you have to take care of, that quotient bits should come within their allocated storage space. So if you have allocated k bits for quotient, and your quotient is greater than your k bits, then this is called an overflow condition, and that's an error, and the results are incorrect then. And looking at a simple decimal number, like a simple base 10 number, like 248. So if I'm looking at dividing this number by 13, right? So here you have to look at what is, how many bits, how many digits do you have for the divisor. So if that is 2, then this means you have reserved the same amount of digits for the quotient and for the remainder, right? And you have double the digits for the dividend. So here we have got 3 digits, but obviously then we have one more digit over here, which is 0, right? Now the first thing that you have to look is if you have got 2 digits in your divisor, then you have to look at the first 2 digits of the dividend. Remember that you have to first of all ensure that this is written in the same format as, for example, if this is 2 digits, then this is twice the size of this, so it should be 4 digits, right? So if it's written in a 4 digit form, then you have to look at the first 2 digits. Now the idea is that these 2 digits should always be less than the divisor. Now if this is true, then this means that your answer, the quotient bits, are going to also come within these 2 bits, right? So if this is true, then this means that the quotient or your answer is also going to come in 2 bits, in 2 digits or bits, whatever. But if this is not true, then there is a problem. So I'm going to look at one of the example is 13 divided by 248, and okay, so you can do it yourself as well. um, can anyone give me the answer? What would that be? So we have got a 1 over here, we will have a 13 over here, and that is going to give us something like 11 and 118 over here. So 118 means 13, 52, and 52 would be 104. So that would be 8, I think so. Yeah, 8, I think so. 13 into 8 would be something like,
Not two, 39 is 117.
okay, 39 is 117. Okay. Okay. 39 is 170. Okay. So that's good because it's okay. So your quotient, your remainder is within 2 bits. Your quotient is within 2 digits. So everything is fine because of this. Now let's take it the same thing, 248, but this time I'm going to have a different number here, 248 and 13, the same thing here, but this time I'm going to have it as 2480. right? So the same thing that we have to look at is two digits here and two digits here, because now it's written in four digits form. So now you have to ensure that 24 is less than 13. Now this is not the case. Now, if this is not the case, this means that the answer cannot come in two digits. It's going to come, it's going to be a valid answer, but it's going to take more than two digits in quotient. Obviously, the remainder is always going to be the same as the divisor because it's less than the divisor. So, but the quotient can be greater than the divisor or it can be less than divisor, but the number of bits reserved for it are insufficient. So this is the first check that you have to do, and that's called an overflow check. So let's come back to our problem here. So let's take an example, a very first example of unsigned division. So all of these are positive numbers, and we have a right shift algorithm over here. So remember, then we were talking about multiplication. We said we had a right shift algorithm or a left shift algorithm. In division, we only have a right shift algorithm. A left shift algorithm. In division, we only have a left shift algorithm. We don't have a corresponding right shift algorithm. So I'm going to come to that algorithm right now. So this is our dividend here. Uh, 0 1 1 0 1 0 1, and we are talking about unsigned numbers, so they are all positive numbers, and this is our divisor, right? Now, in division, and if you're talking about binary numbers, you have two options: either to subtract, either to multiply it with zero or multiply it with one, right? So if you know, if you're going to multiply with zero, then you're not going to get any answer, so it would be zero. So you are going to multiply it with one, and that means you have the divisor itself, and you want to subtract the divisor then from the partial remainder. And this is the process that we are going to repeat many times till we get an answer. So for binary, it's easy because they are just zeros and ones. If you're talking about digits, then you have got many possibilities to divide a number from, and then things get a little difficult. But when you're talking about binary numbers, it's quite easy. You either divide it by you either multiply it by zero or you multiply it by one. When you're talking about multiplication, I'm talking about this equation here that we had here. So what we are going to do, we have our divisor. We are going to guess the quotient. Right, so we are going to guess. So this is how division works, because you don't have a specific number, you don't have a specific equation that can be solved very easily. So you're just going to start guessing. And when you have binary numbers, the quotient values can be either zero or one, right? So individual bits. So we're talking about individual bits here. So you know that if it's going to be something like this, then zero is not going to help you. So you are always going to divide it by or multiply it by one. So in other words, what we are trying to do is an operation called as trial subtraction. So we are going to try the subtraction process. So it's called trial subtraction. So we are going to uh, try out subtraction. If our result is positive, then this means that our subtraction is correct. And then we are going to put a 1 over here in quotient bit. If we get a negative result, so this is when we get a positive result after subtraction, this means that the number that we have subtracted it from was bigger than the divisor, the shifted divisor. So that's why we have a 1 over here. If we get a negative answer, we are going to put a 0. And then additionally, we know that we have done it wrong. So we shouldn't have done a try subtraction for this case. So we are going to restore it. Restore means that we are going to put the value back, the same thing that we have subtracted our results from, right? So I'm going to come to that. So let's come to that. So that's why its name is restoring division. So this is our sorry dividend here. This is our dividend here. 0 1 1 1 0 1 0 1. So it's 8 bits, and we have 4 bits 1 0 1 0 as the divisor, right? Now when we know we have to do trial subtraction, which means that we have to add its 2's complement number or its negative. For example, if this is 10 and you want to subtract something, you want to actually subtract 10 from something which is, you are going to add minus 10, right? So that's the same thing. So what we do is we have its 2's complement also ready with us. So if this is d, we should have minus d with us as well, right? So we are going to compute this minus d as well, because this would be used for subtraction operation. So this is the number that we have to add, right? So remember, we have to subtract in division, but instead of subtraction, we are going to prefer addition process of the 2's complement of the divisor, right? So when once we have the divisor with us, we are going to calculate its 2's complement number as well, and this would be the one which we are going to add, and that's written over here, right? So it's shown here 2 raised to power 4d, which means that it's a shifted divisor. You can ignore this 2 raised to power 4d. The main thing is d is this value, which has been shifted 4 times to the left, and this is going to ensure that you get the right answers when you're going to add or with these numbers. So remember, the process is addition, but it's actually subtraction. So subtraction of the 2's complement of divisor, which means you are subtracting it, right? So let's start our process. This is our first step here. Now in the first step, so what we have here is the partial remainder represented at S. The remainder is represented here with S, and there is a 0 over here, which means that this is the first step or 0th step over here, right? And the first thing we have to do is copy the dividend as it is into the bits reserved for partial remainder. Okay, remainder is going to come in k bits, but we have reserved initially 2k bits for remainder, and this is eventually going to shift to the left after 4 steps, and we are going to get our 4 bits, right? So but what the first step is that the same thing is copied in the partial remainder register, right? Remember, in multiplication we copied 0 over here. We started with 0, but here we are going to start with the same thing. The dividend is going to be copied into the partial remainder register, which has to be shifted to the left. Now the first step is to shift left. Okay, so in multiplication we added and then shifted, but here we are going to shift left, and this is also because it's a left shift algorithm where shifts happen first. So the first thing is we are going to shift left. So you can see here that everything moves 1 bit to the left, and then we are going to do trial subtraction, right? So this is our first step, trial subtraction. Now when you're talking about trial subtraction, we are adding the value of the negative of divisor with this number, right? Okay, so you can assume here that there would be zeros over here, so you don't really have to add anything to this part. So you can limit your adder to only these bits at this point, right? So let's do the addition. If there are any carries, ignore them, because we have taken these extra bits to represent carry. If there is anything out of these bits are going to be ignored. So let's try to add. 0 plus 0 is 0, 1 plus 1 would be 0, and 1 carry over here is 1 plus 1 plus 1 would be 1 and 1, and 1 carry over here. So 1 plus 1 would be 0, and 1 carry over here, and 1 plus 1 would be 0. So forget about anything going out as a carry from this point onward. So the answer that we got is 0 0 1 0 0 1 0 1, right? Now this is a positive number because there is a 0 over here. So in 2's complement number, if the MSB is 0, then it's a positive number. If the MSB is 1, then it's a negative number, and we have talked about that, because if the MSB is representing a negative weight, so if you have a negative weight, any other bits added to it cannot change that negative weight to a positive weight. Even though if all of them are ones, they can never change that higher weight. So this is going to be a positive number because its MSB is 0. Okay, so before that, I forgot to mention that the first thing that was that we have to do in division algorithm is to check for overflow, and we have checked the overflow like this. We have taken the first 4 bits over here and the first 4 bit of divisor, and we have to ensure that the divisor is bigger than the first 4 bits of dividend, and if that is the case, then there won't be any overflow. So we have discussed about that, but I forgot to do that here in this example. Right, so this is obviously going to be the first step, and then we are going to continue with. So if you get an overflow condition, you can stop over there. You can say just this cannot happen. The algorithm is not going to work because the results are going to be incorrect because of overflow. So the first thing that you have to do is check for overflow. If there is no overflow, then you can continue. Okay, so we have come to the first step, the end of first step. So we added this and we have a result which is positive. So what is the conclusion here after first step? So we did a trial subtraction and our trial subtraction was correct. So if we get a positive number, this means our trial subtraction is correct, right? So so this means that the quotient bit should be 1. Okay, and which quotient bit should that be? Since this is in the left shift algorithm, we are always talking about the MSBs first. So we are talking about Q3 here. So it's not Q naught, it's Q3, right? The first bit would be selected first, would be set first. So the Q3 is going to be 1, right? Okay, so let's move on. Any question up till now? So I've just gone through the first step. Any question up till now for restoring unsigned division? Yes, Fahad?
Sir, it is clear, but can you please again tell that how we have taken the Q3?
Okay, so we are talking about left shift algorithm, and when we are talking about divisions, so what happens in division is if you have to divide something like 240 with 3, you always go for the first bits, the MSB side, and you always try to find out the most significant digit first, right? So you talk about the most significant digit first, and then you move on to the next one, right? So in a left shift algorithm, division only has a left shift algorithm. There is no right shift algorithm in division. You cannot start from this side and move on. So here we have a left shift algorithm, and the first thing that we have to define is the MSB, right? And then we are onward move on to the lower bits, right? The same thing is happening over here. So when we are talking about this case here, so the first step is going to determine whether you have set the first bit as 0 or 1, and that first bit is actually the most significant bit. So it's not going to be the least significant bit first, it's going to be the most significant bit first. If you remember the left shift algorithm we discussed for multiplication, that was also determining the MSB side first. In a left shift algorithm, we're talking about doing it from here and shifting it to the left. So in that case, we are talking about always doing from MSB sides, and that's why we are going to figure out the MSBs of the quotients also first, right? Okay, so Q3 is set as 1. Now let's go to the second step. Okay, so once we are here,
Sir,
we are
just a little bit. Sir, you are saying that if we have a positive number in the S1, then it would be quotient would be 1, right?
yes, that's exactly
Okay,
true.
okay, yeah, clear, clear.
Okay, that's right. So what we did is we did a trial subtraction, and our result is positive. So in other words, let me just do it with one more example here. So let's talk about. So I don't want to go for binary numbers. I want to just go on with some other examples like. Um, okay, so let's try to divide 42 by 3. Um, okay, so the first thing we have to do is go with 1, right? So in a decimal number, you have 1, 2, 3 till 0, 1, 2, 3 till you go till 9, right? So you can go till 9. There can be different possibilities over here, right? It gets a little difficult in talking about decimal numbers, much easier in binary. So how are you going to do that? So what we do is we try out every one of them, right? Until we reach a point where we get a negative answer, which means that this number was greater than that. So we are not going to go through that number. So let me just do it with 142 rather than just 42. Let me just go with 142. and let's assume we have enough space for quotient. So how are you going to do that? So we are going to start with 1, right? We are going to start with 1 and we are going to get 14 minus 3, and this would be a positive number, but it's going to be a very big number, right? So again we are going to increase the value. So 1 can't be an answer, so we are going to go with 2. So instead of 1 we are going to go with 2. So this is going to give us 6, again a positive number in our try subtraction, but it's going to be a bigger number than divisor. So likewise we are going to do the trial subtractions with different numbers. So uh, then we are going to have 3 as well, right? And then we are going to have 4 as well. 4 is going to give us 12, right? Again a positive number. So we are not interested in positive numbers, we are interested in negative numbers. So we are going to go to then 5. So if you are going to go to 5, what we are going to get is 15 over here, right? So we are going to have 15 over here, right? And this is going to be negative, right? So at this point we would know that uh, this operation has gone wrong. Okay, so we should go back one more bit. So it shouldn't be 5, it should be the last one, which was so the first negative that you're going to get means that the previous one was correct. Okay, okay, so instead of 5 it should have been 4, right? So what we are doing is just subtracting and looking for sign, subtracting and looking for sign. Once we reach a negative answer we say, okay, so the last one was right. Okay, now if you're talking about binary numbers, you just have an option of zeros and ones. So you have zeros and ones, right? So you're never going to multiply it with 0 and then subtract it. So you're going to do it with 1, right? And if your subtraction was negative, your result is negative, this means that you shouldn't have done that as well. So for that you are going to go with 0. Otherwise, if your subtraction result is positive, this means that this was correct and you should have answered it as 1. So this is how we are doing it. So we are doing a try subtraction. If we get a positive answer, this means 1 is correct. If we get a negative answer, this means 1 is incorrect and it should have been 0, right? So we have to go 1 digit or 1 bit before that. So if it was 1, then the 1 digit before that is 0, obviously, right? So this is how we are doing it in binary, that we are talking about doing a subtraction each time. In every step we are going to do a trial subtraction. If we get a positive result, then this means the subtraction was okay. But if we get a negative result, then we are going to see what to do. Okay, so let's look at this was the first step, and then uh, we are going to do a left shift before starting the next step. The first thing that we are going to do is do a left shift. So we have done a left shift here, right? And then again we are going to do a trial subtraction, which is to add the 2's complement number of the divisor. So we are going to add 10110 to this number here, right? Let's look at the result. So 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 0 is 1, and 0 plus 1 is 1. Now this is a negative number, which means, in other words, that this number is actually less than this number. That's why it's giving us a negative result, right? So if you want to look at in its actual decimal form, this thing is 9. Forget about these 2 bits for the time being. This thing, these 4 bits are 9, right? And this is that what you are subtracting is 10, right? So you were adding minus 10 to it, but what you are subtracting is 10. So 9 minus 10 is always going to be a negative number. So 9 minus 10 is going to be minus 1, and this is what we get also, minus 1 on this side here, right? So this is going to give us a negative answer. So if you get a negative answer, this means you shouldn't have subtracted. Okay, you shouldn't have subtracted. So what we are going to do, we are going to restore it. That's why its name is restoring division. So if we get a negative answer, we shouldn't have subtracted it, and then we are going to restore it back to its original form, which is over here. Okay, in the next step we are going to start from this point, not this point. So this subtraction is going to be considered wrong, and then we are going to restore it back to its original value, which is this point before the subtraction. So if your result is negative, what you do is set the q bit, the q2 bit in this case, because q3 has been determined, so the next bit is q2. If the result is negative, you set that bit to 0 and then restore it. Restoration means go back to the same uh, value that you had before the subtraction. So we are going to restore it at this point, right? So this is the second step completed, right? So we are going to now start from this, from the third step. So I've talked about positive numbers, I've talked about getting a negative answer. So and let's complete the division and see whether we have obtained the right result or not. So from this point onward, again the same thing, left shift. So this one goes over here, and then 0, 0, 1, 0, and 1 comes over here, and do a trial subtraction, which is to add the divisor and the positive value, add the two's complement. So if you have unsigned numbers, the two's complement will always be a negative number. So we are going to add this. 0 plus 0 is 0, 1 plus 1 is 0, 1, and 1 plus 1 is 0, 1, which comes over here. 1 plus 1 is 0, 1, and then forget about the carries. So what you get is 0, 1, 0, 0, 0, and this one is just copied from this point. So again, a positive answer. So if it's a positive answer, set that bit to 1, and this was a good trial subtraction, so your trial was good. So you set that bit to 1, and then move on, which is now going to be a last step. So we could do a left shift and then add the two's complement. So again we have 1, 1, 1, 0, 1 plus 1 is going to be a 0, and a 1 which is going to be discarded. That carry is going to be discarded, and then you get a 0, a positive answer here. So positive answer set the last bit q naught as 1, right? So these 4 bits here are the remainder bits. So these 4 bits are then your remainder bits. So after 4 steps, so we started with a partial remainder which was equivalent to the dividend in the first step, but at every step one of the bits was shifted left until we reach to the 4 bits left in the remainder, in the most significant part of that full 2k bit register. So you're talking about the higher bits over here. So that's the remainder part here. The quotient bits have been selected in every step. So 1011 is your quotient here. Let's try to see what we were trying to divide. So this number is actually, what is this number? So we have a 64 here, and a 32, and a 16. So 64 plus 32 will be 96, and 96 plus 16 would be that would be 96 plus 16 would be 112, right? No, 96 plus 16, yeah, 112. 112 plus 5 would be 117, right? So 117 is our dividend. So 117 over here is our dividend, and we need to divide it by 10. So that's an easy thing to do. So you are basically dividing it by 10 here. So you know what the answer should be. So 110 multiplied by 11 is going to be 110, and the remainder is going to be 7, right? So this is going to be your answer. So your quotient should be 11 and your remainder should be 7. So what we see over here is, yes, our um, remainder is 7. That's the remainder, and our quotient is 1011, which is 11. So this is true, right? So we got a right result. We got a correct answer. Uh, yes, any question up till now?
So it's not a question; it's a clarity.
Hmm.
Whenever we have a negative number in the remainder, just as we have in the S2, when the
Hmm.
quotient is 0,
Hmm.
then we won't add. We would just shift left, right?
we would just restore. We are going to restore it. We are going to ignore that result. That
Ignore that
result.
result. That means that the previous result, which was in S1, that would
Yeah.
come down as it is, right?
Yeah, the previous result that was actually that had been subtracted, right? So that's going to be restored back. So S1 was shifted left once in the next step, and then it's going to be added with the two's complement value, right? So
Yes.
that value is going to be restored back. So what we are talking about is restoring the same thing over here, right? So this result is wrong because it's a negative result, so we cannot do anything with this result. So we are going to restore this before that result was before the subtraction operation. So we are going to restore the same thing back, and then we are going to continue. So continue means to left shift and then subtract. So we cannot continue from this point. So we are going to restore S2 to the previous value that it had at this point. So that is restored in this step, and then we are going to continue.
Got it, sir. Thank you.
Okay, thank you. So, but this division algorithm is only for unsigned numbers, and that's why it's quite simple. Once we have looked at the way it's going to work, then we need to shift it to a hardware divider to see how a hardware divider can be built using this. So if you people are clear of these steps, now what's happening when we are talking about restore? How can we do that at hardware level? So when we say we are going to restore it, there can be two things that you can do to restore a number. One thing is, if you have done a subtraction operation like this and you have obtained this answer, what you can do is, and you want to restore, what you can do is you do an addition operation, right? So if I'm going to add the same thing back to this number, I'm going to get the previous number, right? So if I subtracted something from it and I'm going to add the same thing to it, I'm going to get the previous answer. So that this is one way we can restore and get the same result back, right? But this means that you are going to do two operations. One is the regular operation, then the try subtraction, and then when you find out that the result is negative, you do an additionally. So that means that's an additional operation, and it's going to take more time for that. The other thing is, what you can do is, when you're talking about registers, they have a load signal, right? So they have a load signal which tells them when to load something which needs to be stored in a register, right? If you disable this load signal, this means that the data that is coming in cannot be stored in the register. So this means it's holding the previous value that it was holding at that time. So we are going to go with that particular restore operation. So the register were holding this when we started this addition operation. And at every new step, what we do is we load the new value in that register so that the next operation starts from that point. But when we find out the result is negative, we are going to disable the load operation. So nothing is going to be loaded into that register. So we have the previous value already there in the register, right? So this is how we can do the restore operation. So I'm going to look at the hardware part of this. So this is the hardware divider. So I'm going to give you some time to go through this yourself. These are the quotient bits that are going to be. So I'm going to, yeah, these are the quotient bits here that are going to be determined after every step. And the first bit that we are going to do, since it's shifting left, so the first bit has to be the MSB, because after that much steps, that bit is going to come at its right position. So MSB is going to determine first, and then it's going to move on to the left till it reaches its right position. This is your divisor register, this is your quotient register, and this is going to be your shift register, right? And this is actually the dividend itself as well. So what we are doing is we are doing our operations on the dividend, we are taking the first half or the ms, the most significant half of the dividend, like we were doing here in our algorithm. So we were basically concerned with this part only. So if the dividend is copied over here, so this thing, the whole thing, it doesn't matter. So we are talking about shifting only this part. Okay, shifting is done on the whole register, but addition is done, the subtraction is done on only on this part, the most significant part. So the same thing is over here. Okay, remember that these additional bits were basically just introduced for looking for the right signs, because this is an unsigned division, so you don't need these extra bits in the hardware divider. You know when to subtract and when to add. So this adder is, you can see here, it's a constant one over here, which means it's only doing what? Subtraction. And the divisor is introduced with a complement, a negative bubble over here. This means that it's doing a ones complement, a one coming over here. So this means this adder is working as a subtractor. So you are subtracting these two values, right? In our algorithm, we were adding the two's complement. That's the same thing happening over here. You're calculating the two's complement like this, and you are doing the addition for here. And that result is going to come into that particular portion over here only, and then it's going to be shifted. So that's the same thing happening over here, that the result is going to be loaded into this part, and then we are going to shift it to the left. um, One thing that I need you to just go through it, I've written it also over here, is just you just have to verify. There is a trick done over here. It's basically an OR gate over here that's going to give you the right quotient bit. So in two's complement arithmetic, adding a negative value to a positive value always produces a C out of 1, right? So if the result is positive, so if the result is positive, that C out is always going to be 1, and then we need a 1 coming and on the quotient bit. So we have used an OR gate. So if you get a positive answer or you get a positive result in this side, that quotient bit is going to be 1, right? So you can go through this circuit yourself and see how this OR gate works by taking different examples. So it's a very simple circuit. It's going to work obviously one bit at a time. So there are shifts operation over here. It's a sequential design. So you're going to work on different cycles, but it's a very simple restoring um, unsigned divider, unsigned number divider, right? Okay, so if you have any questions, just go through the circuit once more, or maybe even once I've given you the slide. So it's not a very difficult thing to do. And I'm going to not give you an exercise on restoring hardware divider, restoring division to do on your papers, on papers and pencils with you. But I'm going to go to another algorithm, and then we are going to practice that second algorithm, which is for unsigned numbers, for signed numbers as well. So I could have given you an example to solve it at this point, but since we have to cover a lot in this chapter, in this lecture, so I'm going to move ahead. So if there are no questions, then I can just go on to our next algorithm, which is non-restoring division algorithm. So up till this point, we are talking about restoring division. Now we are going to talk about non-restoring algorithm. So when we talk about restoring division, so what happens in the different steps? So we shift the registers, right? We allow the signals to go to the adder, the results to go to the adder. We determine and store the next quotient digit, right? And when we are talking about restoring division, we also have to look for whether or not we have to store that trial difference. Okay, so whether to load or when not to load, right? Now looking at all these steps, you can say that it's not a problem to do these in a sequential way. Shift the registers and add those two numbers, and then there is in 3 and 4, you can see that there is something that you have to do and sometimes you don't have to do. Like 3 is something that, okay, you are always going to do. You are always going to determine what is the sign, is it positive or negative. But in 4, there is something different each time. So sometimes you are going to store that value, and sometimes you're not going to store that value. This means that 4 is dependent on 3, right? So you are waiting for that result, and then you can do 4, right? That's restoring division, because sometimes you're going to load it, and sometimes you're not going to load it. Okay. So what happens when you're talking about building circuits like this, even a small thing which is sequential in nature is going to cause problems by lengthening the clock cycle. So if you talk about the clock cycles, which is determining how these operations are happening one after another bit, so this fourth step is really problematic, because it's waiting for the result and you cannot improve that thing. So a non-restoring algorithm is going to take care of that. In this algorithm, we are not going to restore the result back. So at every point we are going to load something, right? So we don't have to worry about whether we have to load or we don't have to load. At every step we are going to load something. So if we get a negative answer, we are going to load that as well, right? So what happens over here in non-restoring division algorithm is we are still going to do the trial subtraction. So if the result is negative, right, we are still going to load that result, which means that the result is incorrect, right? But we are going to make that correction in the next step. Okay. So if we get a negative result, we are still going to load that, but we are going to correct that in the next step, the very next step, right? So I'm going to come to the non-restoring division algorithm. Let's have some justification why this is going to go true. So why is it good? Why is it possible or acceptable to store an incorrect value in the partial remainder register? When you store a negative value, that's actually an incorrect value, right? So when we're saying that we were talking about this number over here, dividing by 5. So we subtracted 15 and got an answer -1 over here. So the thing is, we are saying we can leave it with -1 and carry on with 2 at -1 and 2, and then do a combination of that and make up with a second step, right? So this is something that we are going to see how it's done. Right. So why is it acceptable to store an incorrect value in the partial register? So let's say we have um, a partial remainder at the start of the cycle, and we denote it as u, right? So what we do when we have this partial remainder at the side of cycle, so we have already shifted it, right? So we need to subtract it. So we need to do the trial subtraction. So if you do a trial subtraction, it's actually subtracting 2 raised by kd, which is the shifted divisor. The divisor shifts to the most significant part of uh, most significant part. So it's as if you have subtracted the shifted divisor with u. So you are doing a trial subtraction, which is u minus 2 kd. Now the restoring division algorithm was restoring the correct value if this result was negative. Now, this is the first option. So if the result of u minus 2 kd is negative, right? So what are we going to do? So we restore the partial remainder to its correct value u. So if this result is negative, we ignore this negative result and we correct it to u. In the next step, what we do is shift left, so u becomes 2u, and then subtract to get 2u minus 2 kd. So in each step, we are doing a trial subtraction of 2 kd. So what happens if you get a negative answer, you correct the value. That's the restoring part. In the next step, you're going to shift left, and then you're again going to do a trial subtraction. So in the next step, what you are going to get is 2u minus 2 kd. The other thing that we can do, and that's the topic of non-restoring division, is keep the incorrect partial remainder 2 minus u minus 2kd. So if this is negative result, leave it as it is. In the next step, shift it left. So if you're going to shift this whole thing left, so the whole thing becomes twice of this whole number, and add that to get the same result. Okay, so I'm going to do that once more. So what I'm trying to say is, if you have had a partial remainder u at any step, and you are doing a trial subtraction, right, and the results got wrong, so you are going to restore it back to u, right? In the next step, you are going to shift it left and do a trial subtraction again in that next step. So that was option number one. The option number two is leave this thing as it is, do a left shift. So the whole left shift means twice of the whole thing, right? Now, here, and when you're talking about not in the restoring division algorithm, we were doing trial subtraction in all steps. But in this case, when we had a wrong partial remainder, so in that step, in order to correct it, instead of doing a subtraction, we are going to do an addition. So if we are going to add 2kd to this number in the next step, so what we are going to get is 2u. So minus 2kd plus 2kd is going to be minus 2kd, which is the same thing that you were obtaining from the restore individual algorithm, right? So the basic idea is the end result would be same, provided instead of doing a subtraction, you change the operation to addition. Okay, so again, addition and subtraction are the same thing. Okay, addition and subtraction are taking the same time because they are being done by the adder. So that's not a problem. The problem was that particular load. So we were talking about either to load the register or not to load the register. That problem has been resolved in non-storing division. So we are always going to load. So we are not waiting for the step number 4. So this means our clock cycle can be lowered down. It can be made faster. Okay. So non-restoring division is going to be faster than a restoring division algorithm. Okay, so let's look at another example over here. Okay, so that's the same example. That's the same example that we did for restoring division. Let's try to see how the things are working in this case. So that's the same example. So the first thing we have to check is if there is no overflow. So first 4 bits with first 4 bits over here, yes. So the divisor is bigger than that. So this means there is no overflow. Additionally, we have written down the 2's complement of this, so that we have to do an addition with this number, not a subtraction with this number. Okay, so first step, again the same thing. The dividend is copied in the partial remainder register, and in each step it's going to be shifted to the left, so that we get a final answer. So the first step is shift left. So we are going to shift left and do the trial subtraction. Okay. So when we do the trial subtraction, we are adding the 2's complement value. So it's going to be 0, 0, 1, 1, 0, 1, 0 plus 1, 1 carry, and then ignore that carry. So you get a positive number, and we got a positive number there as well in the first step. So if it's positive, set that Q3 bit to 1. So that's the same thing up till now. Okay. Again, shift left. So if you're going to shift it left, so you have got this number, do a try subtraction. So this was the part where we got a negative result. Let's see what happens here. So we have 1 plus 1 plus 1 plus 1, 1 plus 0 is 1, and 0 plus 1 is 1. So we have got 1, 1, 1, 1, 1, 1, 1. This is a negative result. Now, in a restoring division algorithm, we restore it back to this point. But here, in non-restoring division algorithm, we are not going to restore it. So we are going to continue with this, right? So we are going to continue with this, but in the next step, instead of doing a try subtraction, we are going to do an addition. So the steps remain the same. We are going to still do the left shift. So we did a left shift 1 1 1 1 0 1, right? But here we are going to change because it's a negative number. So we are going to change our operation to add instead of subtract. So we are going to add the divisor itself 0 1 0 0 1 0 0 1 0 1 0. So we are going to add that instead of adding its two's complement. So this means 0 1 plus 1 0 1, 1 plus 1 0 1, and 1 plus 1 plus 1 1 1, and 0 and 1. Again, a positive number, which means the set q3 q1 as 0 1, and do a try subtraction. And finally, you can see here we obtained the right the same result here. So it's 7 and it's 11, right? And this thing is not restoring anything as well, except that whenever we get a negative result, we are going to change that particular operation. We are going to change that from addition to subtraction in the next step. Okay.
Sir, when the answer comes negative, then we do not restore it, and in the next step we do addition of like in this example we have 10, so we'll add 10 again.
Yes, yes, that's right.
Thank you.
That's right. Um, okay, so the same thing here. What we are doing is 117, and we were dividing it with 10. So in each step, what we are doing is actually we are subtracting it with the shifted 10. So we are shifting it 4 times, which means we are multiplying it by 16. So in every step, what we are doing is we are subtracting it with 160. Okay. The same thing was done in restaurant division algorithm as well. So this step here 2 is 4D is actually 160. So we are subtracting minus 160 with every partial remainder at each step. And sometimes we are going to get a negative answer. Sometimes we are going to get a positive answer. So if we get a positive answer in a restoring division algorithm and in a non-restoring division algorithm, we do the same thing. We set that qubit as 1 and continue. But if we get a negative answer, we do differently in a restoring division algorithm and non-restoring division algorithm. In a restoring division algorithm, we restore that negative result to a positive result back to its original value, and then continue setting the qubit as 0. But in a non-restoring division algorithm, we just set the qubit as 0 and change the operation from subtraction to addition in that next step. And this is going to ensure us that our result is going to be true. So another way to show this graphically is like this. So I'm going to just try to just zoom it over here to tell you the restoring part first. So let's look at the restoring part. What's happening in the restoring part? Now we started with 117, right? We started with 117. The first step was to left shift. So 117 left shifted by 1 is going to be as if we have multiplied by 2. So 117 actually becomes 234, right? So 117 here, and if we shift it left, it becomes 234. And in each step, what we are doing is we are doing a trial subtraction, which is subtracting it with 160. So as I've shown you, 10 was shifted left to be 160 here. So 234 becomes after subtraction 74. That was your first step, 74, right? Do the same thing, shifted left, so 74 becomes 148, and do the trial subtraction, 148 becomes 160. Now you get a negative result, which is minus 12. So in a restoring division algorithm, if you get a minus 12 over here, you're going to restore it back to its original value. So 148 becomes 148, and then you're going to continue from this point in the next step. So shifted left, so 148 becomes 296. To do a trial subtraction, which means 296 minus 160 you get a positive result 136. Again, shifted left in the next step to 272, and shifted left to subtract to get again 112, which is a positive. So this 112 is actually the shifted remainder. So if you're going to divide it by 16, you're going to get 7, right? Because this is a shifted remainder. So we should have obtained 7 over here. So if you are going to divide it by 16, you're going to get 7, right? So the final answer is 112 in this case. Now let's look at what's going to
Why
happen.
then dividing it with 16 in the last step to get 11? I didn't get the last part.
Yes,
Is it
because this number, yeah, this 112 is actually the first 4 bits. We are taking the first 4 bits as the remainder. So 112 is actually 0 1 1 1 0 0 0 0. So the last 4 bits are 0, which is the shifted part, and you're taking the most significant byte of that remainder register, and that byte is going to be 7.
okay, sir? Okay.
Do you get this thing? Because okay, I'm going to come to that again. Now, when you're talking about a non-restoring division, what's the difference in these two? Now, if you got to talk about non-restoring division, 117 is again started with 117, multiplied, shifted left to get 234, subtracted, did a 12 subtraction, 160 subtracted from it, we got 74. Then we multiplied, shifted left by 2 to 74 becomes 148. Did a try subtraction and got an answer negative, which is minus 12, right? And now we are going to continue with minus 12. So we are not going to restore 148 with 148. That was the step of the restoring division, but not in non-restoring. So we are going to continue with minus 12. Shifted left. So minus 12 becomes minus 24, right? So then instead of subtracting, we add 160 to it. So if minus 12, 24 is added to 160, you're going to get 136. And you can see over here that's the same thing, 136. So you have restored it. You obtained the right result in the very next step by changing the operation from subtraction to addition, right? And the remaining is the same thing, which is also over here. So that's the only difference here. So we are restoring it to 148 and continue. So in every step we are doing a try subtraction. The problem is that sometimes we have to load, sometimes we don't have to load. That's going to make a cycle a little problematic because we are waiting for that result, and it's a sequential, going to be a sequential step. It's going to take some time. But here we are not waiting for it. Uh, we can preset our load signals. So if you're going to preset the registers, this means the delays for loading and unloading, the decisions are not required, and you are free to do that work in parallel with something else. So you are going to set that signal of load earlier in time because you're always going to load it, right? So this is going to give you the same result in the very next step. So it has corrected it. Anyone, any questions here? Any questions here? Okay, so you were talking about 112. I'll say that your mic is on. Do you want to ask something? Okay. Okay, so you were talking about 112. So 112 is basically what we are talking about is 112 is a shifted 7, shifted 7. In this case, you can see over here. So this is your answer, 0111, and there are 4 zeros as well over here at this point. So if you're talking about this thing as a whole register, it was initially 117. So we started with 117, and these values that I was showing you graphically were actually the values that we are doing over here, right? So this 0111 has got 4 zeros as well over here. So that means you are having this value is then going to be 112, where you are adding 64 plus 32 plus 16. That's 112, right? So that's the last value that we obtained, and we are going to take that higher bar, and that's going to be considered as our um, remainder bits. Okay, so this was how we can say that restoring and non-restoring are both going to give us the same result. Non-restoring is going to be a little faster than restoring division, right? Okay, so up till now we have discussed about only unsigned numbers. Now we are going to look at signed number division. Now signed number division is a little tricky, and it's not really easy to do sign division because sometimes you might not get to the right answer, so you need some correction steps, right? And this is because division is not a simple thing to do. Like, we have an equation to solve, so division does not have simultaneous equations to solve and you get the answer, because there are two unknowns. You do different trials, and that trials can go wrong, and sometimes you don't get the right result. Okay, so before I go with sign division, let me just go through sign division here. So let's say we need to divide 14 by 3 here. Okay, so what's the result? Anyone? Yes, anyone? Mohammed Imtiaz?
Yes, sir.
Yes, what's the result if we divide 3 by 14?
We can threefold
We are going to have a 4 over here, and a
one is
quotient, and a quotient of
two.
quotient is 4 and remainder of 2,
Yes, sir.
right?
True.
Okay,
Yes, sir.
okay, thank you, thank you. Okay, so what I'm going to do is I'm going to have some uh, negative numbers now. Okay, so I'm going to have some negative numbers now. So I'm going to try with minus 14 and 3, and I'm going to try with minus 3 and 14, and I'm also going to try with minus 3 and minus 14. Okay, so yeah, the equations were discussed in our first frame, where we were talking about what was that? Okay, so we were discussing about that here. So these are the equations that we have. Z is equals to d into q plus s, and d should always be greater than s. In other words, remainder should always be less than divisor, right? So we are talking about the last one. Yeah. Okay. So the equation remains the same. What should be the result of this? 3 into minus 14. Okay. Okay. So 3 into minus 14. So if I do this 3, 4, 12. Okay, minus 4. 3 minus 4 minus 12. And I'm going to get,
minus
sorry, not a plus, a negative over here. So I'm going to get what? Minus 2. Right? Okay, so what if I do this, something like this, minus 14? If I have minus 14 again and 3 over here, so what if I go for minus 5 over here? So if I go for minus 5, I'm going to get minus 15, and my result would be what? 1, right?
so minus 14 and minus 15, two negatives won't add in this.
Yeah, because we are going to do subtraction finally.
Minus minus, whenever there are two minuses, so we do a plus operation, na?
Yeah.
So in this video, you're saying that the answer is 1.
Yes,
Uh,
because
bit
it's going
minus
to be
20.
minus 14 plus 15.
Minus into minus becomes plus.
Yeah.
Oh, okay, okay.
We are doing a subtraction in every step. When we're talking about division, we are always doing a subtraction. I'm just saying, if we are going to multiply 3 with minus 5, we are going to get minus 15, right?
And minus
And
15.
we are still going to do subtraction. So if we are going to subtract minus 14 by plus 15, I'm going to get 1. Now,
Okay, I got it.
let's just remember our equation. We had the equation z is equals to d into q plus s. So both are satisfying this thing, because z here is minus 14 and this should be equal to d into q. D was 3 into q is minus 4 in this case, plus s, which is going to be minus 2, and in this case it's minus 14 is equals to um, 3 into minus 5 plus 1. Any confusion here?
Sir, why are you adding extra minus earlier to minus 12?
This one here,
Yeah, this one.
this is normal operation. This is, we are always going to do subtraction.
Okay,
Yeah, whenever we do, this is the way that you are doing when you're talking about division on paper pencil. You always subtract, right?
okay.
Yes, you all know how to do division, so this is nothing new over here. So we always subtract in every step, right? So this is the subtraction operation. So I'm just telling you. So we get the same answer, right? So 3 minus 12 minus 2 is equals to minus 14, and minus 15 plus 1 is equals to minus 14. So this is true. And then the second thing that we had was d should always be greater than s. The 3 is greater than minus 2. That is also true. And rather what we're talking about is magnitude. So that's is also true. And 3 is greater than 1. That's also true. Yes. So which one to select? Which is the right one? Remember, in division we had an equation and an inequality. So I have written the equation over here. Both of these are getting true for that. I've written an inequality also over here. Both of them are getting true for that as well. But what is the right answer? Should I go with the left one or the right one?
Sir, I guess in which the difference is less. The right one.
This one here. So Shirina says that this is correct. Anyone else? Because this is going to be a problem, because sometimes I'm going to get different answers. So what should be my right answer? I need to have single answer. I cannot have multiple answers. And if I go for something like I need to look for differences, this means that it's going to be problematic,
So,
because
but there should be one more condition, like in the previous questions, we made another condition for that if we were getting two options.
okay. So what should be that condition then? What could be that condition? What should be that condition? Remember when we say that we are having positive answers, the way we had 4 and 2 over here. But here we are getting minus 4, minus 2, that has the same magnitude, but minus 5 and 1 are totally different numbers, right?
So
So
what if we remove the mod sign?
what if we what?
What if we remove the mod sign?
Mod sign, so that's not going to be a problem, because 3 is still greater than minus 2 and 3 is still greater than 1. That mod sign is there because if you don't take that mod sign, so you might get 3 is greater than minus 5 as well, right? But that's not going to be true, because I can get many different answers. Like for example, if I go with something like 3 over here, 3 multiplied minus 3, I'm going to get 9, right? So I'm going to subtract 14 by 9, I'm going to get 5, minus 5. So again 3 is greater than minus 5. But if you're looking at the magnitude, then 3 is less than mod of minus 5. Okay, so that limits me to only a single answer in this case. So it's not going to be many answers, because if I don't have a mod over here, then any number negative is always less than 3. 3 is always greater than that negative number. It could be minus 100 as well, right? So we are going to have this mod because we are talking about the magnitude in this case. Okay, so um, let's have a break, or maybe shall we have this answer before the break? It's better we have this answer before the breaks, and we can go for a small break of 15 minutes. So yes, anyone, which is the right answer? Actually, Akash Ali, you're here. Which of
Yes,
them?
sir.
Yeah, which of them is the right answer in your opinion? You're going to go with this left one or the right one,
So right one.
or you say you are undecided?
Right one, right one.
Right one. So he's also has. So I have got two takes now. Yes, I'll say the Heather. Which option are you going to select? The right one, the right one? Said, are you here? You can even write if your mic is having some problem. You can even write on the chat, right one or the left one. Mohammed Imtiaz, or if
Yes,
someone
sir. Yes,
if
sir.
one if someone says they are undecided, that can be an option as well. Which option, left or right?
Sir, Hail is fasting. I guess he has written on a chat. He is fasting.
You're opting for what, left or right?
I am undecided, sir. But I am.
Undecided.
Yes, sir. Hail said has written something in the chat. You can read it. He is.
Okay, so you are basically undecided at this point.
Yes, sir.
Okay, Fahad Khan.
Yes, sir, the situation based on the conditions are both true. So therefore, they both could be the correct answers.
Yeah, but we need to decide one, because if you are going to do further anything with these answers, the results could be very different. Because if I need to say, for example, do a multiplication with whatever answer I'm getting the quotient with, I'm going to multiply that with, say for example, -1. So that this is going to give me 4 and this is going to give me 5, and any subsequent operation is going to be wrong, right? So we have to select one. So you are undecided as well.
Yes, sir, correct.
Okay,
Yes.
Shirina had this right one, and
I have one confusion. If we are getting the answer with -4, that is satisfying the condition, so why are we multiplying with -5?
no. I'm saying, not saying we are going to multiply it -5. I'm saying, let's say whatever the answer we are getting, we have a subsequent operation, the next operation in which we say multiply with some other numbers. Say for example -1,
So
right?
we also go for a sequential approach and like multiplying with first with -3, -4, and then -5. And if we see that -4 is giving us the correct answer, so why would one opt -5?
No, my question is that if this is the answer that we are getting in the next operation, like for example a subsequent operation, what we are doing is whatever answer we are getting, we are multiplying it with -1, right? So this is the answer that we are getting, and we are doing some more operation on this answer. So sometimes we are going to get 4 and sometimes we are going to get 5. So this is going to be wrong. We need a single answer. So we need a single answer to be selected. We cannot have both of them. So that's the only thing here. Altaf Ali Shah,
Sir, maybe positive remainder. I think the right one is correct.
positive remainder. He comes up with a new suggestion that positive remainder should be selected
Maybe,
always.
sir. Okay.
Okay, but yeah, anything. But I need a discussion. Obviously, I'm not really asking you for any of your answers, because this is the first time we are going to do that here. Yasser Ahmed, Yasser,
So undecided.
undecided. Okay,
Yeah.
so the thing is, let's come back to this, and I'm going to just go on the break quickly. So now, when we talk about positive numbers, we get an answer of 4 and 2, right? So if you want this answer, because multiplication can subsequently be used in different operations, and for example, if you get this answer, you would want that anything which has the same magnitude should always give you this magnitude, right? So your preferred choice is to get this answer, right? And how are you going to do that? So the thing that you have to look for is that the sign of dividend should match the sign of remainder. Now this is another rule. That's the third one. So we have got first one here, the second one here. The third rule that we have to observe is sign of remainder should be equivalent to the sign of divisor. So sign of remainder is sign of S. This should be equal to the sign of remainder, dividend, sorry. So remainder and dividend should have the same sign. This is not the case over here. So this is negative and this is positive. So this means this result is wrong. And you can do
So,
this.
suppose, sir, if we get instead of plus positive, if we get -1 on the right side, then what should be best? Either
Yeah.
-2 or -1.
If you're going to get a -1 over here,
Yeah.
then this is going to be your right answer. But you can never get a -1 and a -2.
So it
Right?
means, as Sharina said, that the least difference will be more preferred.
No. It's not about least difference. You don't have to worry about any differences. You just have to check the signs. You just have to check the signs. So if you're going to come back over here, this is positive. This should always be positive. If
No,
this
no.
is negative,
I mean, sir, if
your
sign were
remainder.
matched, then if sign were matched, then we gauge the difference in between the both ends of.
No. Look over here. In these two cases, these are the only two possibilities that you can have if you are going for the magnitude. Right? These are
Okay.
the only two possibilities. And one of them is going to have a matching sign and the other is not going to have a matching sign. It's always going to be the same. Only one answer is going to have a matching sign. The other is not going to have a matching sign. You can take any example you want. Right?
Okay,
If you
sir.
go for these two first and two, if you satisfy one and two, where 2 is looking for the magnitude, not the value. So in this case, these two are the options only that are satisfying, and in these two cases, one of them will have the same sign as the dividend and the other will have a different sign for the remainder and the dividend. Right? This is for any case that you can select. So if you can even try this way in this one over here. So here also you are going to get, now in this case, since the dividend is negative positive, you should have a remainder also positive. And in this case, since the dividend is negative, you should have a remainder also negative. Right? And you're going to see, if you do this, you're always going to get the same magnitudes. 4 plus 2, right? It's not going to be 4, it's going to be -4. In this case, you're going to get -4 and -2. So you can check it that yourself after a break. So let's have a break. We are a little late. So let's have a break of 15 minutes. I'm going to come till 7:50 now, right? So we are going to take more questions after that. I'm going to stop over here and then we are going to continue.